Alright, so when we're dealing with these enthalpies, we need to standardize everything. We need to make sure we're comparing things the same way. And so what we've done is as chemists, we've defined something called the standard state. And the standard state is defined as the element of the compound in its pure form at standard pressure, which is 1 bar, which is almost 1 atmosphere. And at the temperature of interest, which is usually defined as room temperature 25 degrees Celsius. The way we denote a standard state is with a degree sign. So the standard enthalpy change, in other words, the enthalpy changes when everything is at the standard state, is delta H degree, with a superscript degree sign. That just indicates everything in the equation, in the reaction, is at its standard state. And the standard state is the most stable form at that pressure and temperature. So oxygen would be diatomic, O2, as a gas. Carbon as graphite. Glucose, C12H22O11, as a solid, and so on. The delta H0F, that's how that's read, the standard enthalpy of formation, F for formation, is the enthalpy change for any compound when 1 mole of that is formed from its elements. Which means that for elements, the standard enthalpy of formation is 0, because they're already elements. There's no formation to happen. Usually when you look up delta H's in the back of a book or in any table, you're going to find the standard enthalpy of formation. And we can use that formation, the delta H of formation, to find the enthalpy change of any reaction using Hess's law. Just to review the standards that we use when we're using something like Hess's law. If you reverse a reaction, change the sign of delta H. If you have to multiply a reaction, you multiply delta H or divide it by the same thing. If you are looking for the total enthalpy change, you can just take the enthalpy of formations, the delta H0Fs, of all the products, times their moles, because remember it's for 1 mole, so times the coefficients, minus that of the reactants. So products minus reactants. And again, elements in their standard states are 0. Delta HF is 0. So essentially we just ignore those. This is the fancy equation for the enthalpy change, but it looks a lot more complicated than it actually is. So delta H0 of a reaction, the standard enthalpy change of a reaction, is equal to that sigma sign. And you should have encountered this in math. That weird E is the Greek letter sigma. That means the sum of N, which is the moles, times the standard enthalpy of formation for all of the products. So you take each product, find its delta H0F, multiply it by its coefficient, add all those up, minus the sum of the number of moles, M, times the standard enthalpy of formation, delta H0F, for each reactant, add those up, then take products minus reactants. And it's always products minus reactants. Make sure you get that in your head. Products minus reactants, products minus reactants. Always products minus reactants. Products come first. So when we're defining what the standard state is, and we'll do the sample problem here on the online, if we look at these reactions, we want to try to figure out which of these are standard enthalpies of formation. And let's remember it's the formation from the elements, all in their natural state, of 1 mole of product. So if we look at the first reaction, 2 NAs plus 1/2 O2 gas makes Na2O solid. Alright? So first thing, is the compound being formed from its elements? Na as a solid, that's its natural state. O2 gas, that's its natural state. So that first part is satisfied. The second part is we're making 1 mole. So the coefficient in front of the product should be 1. That's it. It's got 1 in front of the Na2O. And Na2O is an ionic compound, so it would be solid at room temperature. So that first one is the reaction for the enthalpy change of the enthalpy formation, standard enthalpy formation. If you look at the second one, we've got 2 potassiums liquid plus chlorine gas makes 2 KCl solids. Well, let's double check. It's forming from elements, that's right. But we run into a problem with the potassium. Potassium is a metal, which means at room temperature it's a solid. Here we've got potassium liquid. So this would not satisfy that. So the first thing we need to change is we'd have to use potassium as a solid in this reaction. Chlorine gas, that works. But we've got 2 KCl's. The product has to have a coefficient of 1. So we'd have to cut everything in half. The coefficients would really have to be 1, 1/2, and 1 for that. KCl is a solid product, that's right. So 2 things to change in that. We'd have to change potassium to solid. We'd have to cut all the coefficients in half. So we had 1 in front of the product. The third reaction is actually reversed. This is a decomposition. We don't want decomposition, we want formation. So we have to reverse the reaction. Carbon plus hydrogen plus oxygen makes glucose, C6H12O6. Let's check we've got 1 in front of the glucose, so that's right. The other thing we have to check is the states. Carbon in a diamond form is not the most stable. Carbon graphite is the most stable. So we'd have to change that. So 6 carbon graphite plus 6H2 gas plus 3 O2 gas would yield 1 glucose solid. That would make it the standard enthalpy formation. So if we take a look at this sample problem, I want to know the standard enthalpy change for the combustion of 1 mole of benzene. Benzene is a liquid at room temperature. So you'd have to write out the equation for the combustion of benzene, think about what it's reacting with, what the products are going to be, write out and balance the equation, and then look up in the table in the back of your book, the delta H's, delta H0 formations, delta H0F's, for all of your products and all of your reactants. And remember, oxygen O2 would have a delta H0F of 0 because it's an element. There's no formation there. We'll go over the answer to this in class on the next day. For this sample problem, I want you to do the same thing with propane, C3H8. And what you're going to end up finding is the molar heat of combustion per mole. I want you then to take that per mole, find out how many moles 1 gram is, and make that change. So multiply by the number of moles that 1 gram of propane is. Take the answer to the previous sample problem, multiply that by, and use your railroad tracks to figure out how many moles of benzene that is. Multiply by moles of benzene. And figure out which one produces more heat and how much more. Should be fairly simple. We'll go over the answers in class, but please, 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 please try these sample problems on your own. Use your textbook. Use the equation that I gave you in the notes here. See if you can do it before you get to class.